Hi, hey guys, welcome back to another video from Matt's Math Tutorials. Today I have another AMC problem, and this is actually a problem from this year. This is problem 8 from the 2021 AMC 12B. I think it's a nice little geometry problem. Let's get right into it. Three equally spaced parallel lines intersect a circle, creating three chords of length 33, 33, or 38, 38, and 34. I don't know where I got that from. What is the distance between two adjacent parallel lines? So the key thing here I underline is chord. What is a chord? I drew a circle, by the way. This isn't part of the problem, but I just wanted to be prepared. So a chord is any line that goes from one side of a circle to another. And it does not have to be a diameter. Okay, it does not have to pass through the middle, right? So if you have something like this, that'd be the diameter of the circle, but a chord can be from any point to any other point. So we have three of those of length 38, 38, and 34. So let's actually just draw. I think it'd be useful to draw first a diameter of the circle, and then about where we think the midpoint, the center of the circle would be. I think it'd be about right there. Right, that looks reasonable enough, I guess. So now you have chords of length 38, 38, and 34. So these two are the same, which is interesting, right? Because if you draw just an arbitrary chord somewhere, we're gonna do it like this. It could be, it could be like that, but then we'd have to draw another one, like that. Nobody wants to do that. So we're just gonna do this. If you draw one like this, to have another chord that's parallel to this and the same length, there's really not many options at all, right? Because that would be longer, that would be shorter, right? So it looks like our really only option is nothing on this side, but once it starts going back down here, if we draw another one that starts at the same place, just further down, and ends at the same place, just further down, which would be about right here, right? This chord will be the same length. Oops. This chord will be the same length as the other chord. And so if two chords are parallel and the same length, it looks like they have to be on opposite sides of the circle, right? And the same distance away from the center, right? Like that. So let's draw two chords with that in mind. And then we can worry about the third chord later. Oh, I didn't want to undo that part. Okay, so let's draw the first chord. Let's give ourselves some room to work with here. So let's say like that maybe, right? The other one approximately on the other side. So these are, oh, that's better. So approximately on the other side, and we'll call those the 38 chords. And then we need a 34 one. So obviously it's going to be somewhere in this zone because it's going to be shorter. So if we take this distance and just eyeball it up to here, maybe, that looks about right. Maybe a bit higher. So obviously this isn't very to scale, but we'll call that 38. We'll call this 38, 38, and 34. Now, a property of circles that is often very useful is that any point on the circle to the middle of the circle is going to be the same length. So what I mean by that is, look, you start from the middle, go to the edge like this. That's a radius of the circle, right? And that will be the same no matter where you go, as long as you start from the middle. And that property of circles, I mean, that's literally the definition of a circle. And so, surprise, surprise, it ends up being very helpful a lot of the time. So if we want to draw a radius from the center to a point, there's only a few points that really look significant in this problem, and one of them is right there. It feels pretty natural, right? If you're going to draw lines, to maybe draw one to there, right? And then if you're going to do that, you might as well do that for the other ones as well. And then you might want to do one here. I don't really think this helps you all that much, so I'm not going to do it because I just want the diagram to be cleaner for the video, but it'd be completely natural to try doing that line as well if you were just doing this problem. And so now this almost kind of reminds me of something. I don't know if people that take this necessarily know trig. I think they do, but if you're learning trig, you know about the unit circle, right? It's kind of like this. You learn that you have cosine, it's like the x value right here, right? This distance, and the sine is like this value. And this kind of reminds me of that. I don't know if you guys get that vibe from this, but to me it feels very natural to draw a line straight down from here, right there, and another one from here. Because that kind of reminds me of if you had something like this, right? That's kind of what it reminds me of. And then to finish off these two triangles here, I'm going to draw this as a solid line. Wow, okay, that did not line up at all. Sure. Okay, So now we know that this distance here and this distance here are both radii of the circle. We don't actually know what the radius is, but we can still label it as r, and maybe that'll be useful, right? That we know what that distance is. So now we actually know this distance right here as well, right? Because if this is the middle of the circle, let's draw a line that's going straight up and just pretend that that cuts the circle kind of in like a quarter, right? We actually know that this distance here, well, this whole distance here, right, is going to be half of the distance of this, right? Because this is in the middle, it, is a perpendicular bisector, I believe. It goes up straight through the middle of this line, this 38 line. So we know that this distance right here is half of 38, and that, I believe, is 19. And we can actually do the same thing with this 34 line, right? This line going with straight up, it cuts it in half. So this distance right here is 17, which means that this distance down here is 17. So now don't get confused. The 17 applies just from here to here, and the 19 applies from here to here. And so there's another distance that we kind of know as well. This distance right here, yeah, that's a bracket, I guess. We're going to call that x. And so this is half the distance that we're looking for, right? Because we're looking for the distance from here to here, or from here to here. It should be the same. And this is clearly half of that, right? Because we said in the beginning, for the chords to be the same length, they have to be on this, like, they have to be on the opposite side of the circle, but the same distance apart, right? So that is going to be the same as that, which means that if we call that x, then we're looking for 2x, basically. And so if we call this x, then this distance right here is going to be that x plus another distance that we're looking for, which is 2x. So this whole distance right here is actually 3x, and that applies to here to here. So obviously this diagram is getting a bit crowded, so I think we should just draw the triangles, because that I think is really what we're interested in at this point. So I'll draw the smaller one first. It's about like that, right? Nothing crazy precise, obviously. Okay, whatever. I'll just do this manually, I guess. Okay, so we know this is x, and this is, remember, the long one, so this is 19, and this is r. And now if we draw the other triangle, right, we have, it's taller, kind of like this, and kind of like that. And so we know that this is 3x, right? Because it's this distance plus another 2x, which is what we're looking for. And this is 17, right, which we got from this 34, and this is also r. So we know these are right triangles because we pretty much chose to drop this straight down to intersect with that line, right? So we can say that these are right triangles. And now, obviously, with right triangles comes Pythagoras theorem, right? So we can write that out right here. The Pythagorean theorem: x squared plus 19 squared equals r squared. And then same thing over here, right? 3x squared, whole thing squared, plus 17 squared equals r squared. And so at this point, clearly we have r squared here and r squared here, so we can actually just say this part is equal to this part, right? If you want to think about it as taking this and substituting in for that r squared, you can do that. But basically, that is equal to that. So let's write that down here. X squared plus 19 squared equals, I'm just going to simplify this, should be pretty clear, right? You distribute that power, 9x squared plus 17 squared. And so now we just solve for x, right? And remember, we want 2x, right? So don't forget, if you solve for x and it's wrong, remember you have to multiply by 2, because x is just half of the distance we're looking for, right? So if you solve for x, let's see, let's combine like terms here, right? So let's subtract, let's go 19 squared minus 17 squared equals, subtract 1x squared from 9x squared, looks like 8x squared. So remember that the AMC, at least this year's AMC, was a no calculator test. And I do not know the squares of 1917 off the top of my head, so I might rewrite this in easier form. This is the difference of two squares, so you should hopefully recognize that that can be written as 19 plus 17 times 19 minus 17. and that's going to equal 8x squared. And so that's 19 plus 17, 10 plus 10, 20 plus, 16? That's 36, I think. So 36 times 19 minus 17 is clearly just 2, equals 8x squared, divided by 8. 36 times 2 divided by 8 equals x squared. I can simplify this. That's what 72 divided by 8 is 9 equals x squared. And so obviously we want x to be a positive number because it's, a distance in geometry, and negatives don't really make sense for that. So you root both sides and you get x equals 3. But remember, we want 2x, right? So we multiply this by 2. 3 times 2 equals 6. So our answer should be 6. So it looks like our answer is B. All right, so that should do it for this problem. This is a nice little geometry problem, I think. It's not too bad. I think the hardest part is just, drawing the diagram, trying to make it all make sense. And this being problem 8 means that this one shouldn't even be that hard, but this one probably would have taken me a lot of time. I took the A, and I didn't even do well on that, so I don't know how I would have performed on this. But once you get the diagram going, you combine it with this definition of a circle, right, which is, like I said, usually very helpful for this type of thing. It's not too bad, right? The algebra is not too bad. Um, and so, yeah, hopefully this one wasn't too hard. Let me know if there's anything I could do to teach it better. Maybe something I brushed over because I thought it was simple, but you didn't think it was simple, or something that is simple that I took a lot of time on, something like that. Let me know what I can do better next time, because these videos come out every weekend from now until like August or something. So thank you for watching. Yeah, see ya.